For over 2000 years, mathematics had this secret sitting right in the middle of it, this hole. Ancient legends claim that the guy who actually discovered this was drowned at sea for revealing this secret. Early in our childhood, we learn simple things, and this is enough until we encounter something more difficult, something that breaks our understanding of the reality, and that something requires a more elaborate solution. A long time ago, I took a train with my father. I was about 6 years old, and I heard a boy talking to his mother in a train car about a carton of juice. What especially grabbed my attention was not the juice itself, but the way the boy framed his question to his mother. He said, "It is only 1/4 of a liter." And I thought to myself, what an interesting way to look at it. 1/4, it must be a fraction of it, not a full amount. What a smart boy he is, I thought. Many years later, that sounds silly, but that sounds this way only because we become more knowledgeable and more experienced as people. We wouldn't notice that something is different if we lived under the same perspective all the time. The very fact that we treat obvious things as something for granted could be indicative of our knowledge, the demonstration of our experience. But sometimes with this knowledge comes our ignorance, which makes us unable to see the small inconsistencies we would have otherwise noticed if we'd been little, naive kids and treated those things with all seriousness. In school or from our parents, we're taught the concepts of simple numbers. Natural numbers. We're taught the concepts behind them. But who remembers their first exposure to the concept of natural numbers? What did it look like? Do you remember your first book, your first digit, the first number you ever saw? Perhaps not. And neither do I. But I do remember looking at and playing with those objects on paper. We all know from our childhood that we have 10 fingers, 1 nose, 2 arms, and 2 legs. And with time, we stop noticing the way we think about those things. Then we go to school, where we learn the concept of zero, which means the absence of any number at all. Building on this idea, we move even farther, toward negative numbers. The numbers that don't even exist in real life. Or do they? Anyone who lives in a cold country knows that negative numbers can be used for measuring the temperature. This is perhaps one of the most common examples of using negative numbers in real life, although they do sound more abstract than natural numbers. Do you know what is particularly interesting about negative numbers, along with natural numbers? It is that every negative number is actually symmetrical to its positive, natural counterpart. What does it mean for a natural number to be symmetrical to another one? It means when you add those numbers together, you will end up having 0. It has a very beautiful geometric intuition. They are equally distant from a 0. If we try to look those numbers as something unified, how can we treat them? How can we look at them? We can see them as a set of whole numbers. But what is a set? A set doesn't really have a definition. It is a collection of numbers put together under a unified name. Let's call it A. This A would then refer to the group of numbers combined together. Two numbers can never sit in the same set. In other words, duplicates are not allowed. But what about whole numbers in general? What is that? To picture this cleanly, imagine a segment of length 1. We're going to call this as unity. You could use this segment as a gold standard against which to compare other segments and determine how large they are in relation to it. It is called a unity because it has a length of 1. Or, in other words, because it is a single unified object. If you connect many such segments together, you will end up having one long segment whose length is proportional to unity segment. That's because we can add the unity segments many times in a row, chaining it to its own end until we reach the desired multiple. We're going to call this length a multiple of unity. A whole number then tells us how many times the length of a segment is larger than the length of unity. Naturally, we can see that any whole number gives us a segment proportional to this unity. Therefore, any natural number is a whole number. On the other hand, take the negative of a natural number. We know it is asymmetrical to it. Its distance from 0 is exactly the same distance as the distance between 0 and the natural number. Therefore, its length is also wholly proportional to the length of unity. In this sense, negative numbers are no less whole numbers than natural numbers. Although they lie on the opposite side of our line, they preserve the same relationship to unity. But what comes next? What kind of problems do we encounter? Our intuition gives us a hint. If you have a whole number, you can split it into parts. That was something that was noticed many thousand years ago in ancient times. But how long can you continue this process? And what are you going to get in the end? There are so many questions here. And first question, what is the part of a whole? It is exactly what we call by fraction. A fraction is the number that shows how many pieces or equal pieces of a whole you have. For example, if you have a chocolate and split it into two parts, you'll have two halves. Continue this process further and you will end up having 1/16 of a whole part of a chocolate. Such numbers are called fractions. Fractions have different notations. The first one is the ordinary fractional notation, the one that you use and get familiar with in the primary school. And another very common one is introduced a bit later called decimal notation. But how can we create a fraction? Well, it is easy. We just need to take two numbers. The numerator, how many pieces we have, and denominator, how many pieces make up a whole. Our denominator cannot be 0 because we cannot divide 0 into many pieces. That just doesn't make any sense. But hold on for a second. Let's take 2 pieces out of 3 and 4 parts out of 6. Are these the same number? Take a pie and split it into 3 equal parts. Take 2 parts of it. Now take another pie of the same size and split it into 6 equal parts and take 4 of them. You will end up having the exact same amount of pie. In fact, 2/3 and 4/6 are the exact same number. They represent the exact same fraction of a whole, the same fraction of unity. At first glance, however, they look a bit different. The fraction 4/6 is called reducible, but the fraction 2/3 is called irreducible, because the numerator and denominator do not have the common factor that can be divided out. But the beautiful point here is that these fractions and these denominators and numerators are formed from those numbers taken from the set of whole numbers. We have constructed a new set of numbers called the set of rational numbers by applying simple logic following from the necessity of division. Geometrically speaking, all these numbers have a place on the number line. We can place them there, and this is beautiful, because we can see how they will fill the gaps with infinite precision. In fact, there is a remarkable property here. I don't want to spend time proving it here, but I would like to give you a clear intuition behind that. Take any two fractions as close to each other as you like. So close, the distance between them is barely noticeable. The surprising fact is that we can place another number between them. We just take the number which sits exactly in the middle. And between those numbers, which is in the middle and the endpoint, we can find yet another number. And we can continue this process without end, because no matter how small the gap becomes, there is always room for one more number inside it. So it looks like there are no gaps at all. The line appears to be completely full. Well, at least this is how it looks at first glance. But let us put this to the test. Let's imagine a square with each side of 1. Let's draw a diagonal. If we rely on Pythagorean theorem, we know the length of this diagonal is square root of 2. But what kind of number is that? Is there a fractional representation of this number? It avoids precise definition, although if we drop this on a number line, it would be right there. We know that square of this diagonal is 2, so it must sit somewhere past 1. For example, if we take 1.2, its square is 1.96, which is a little less than 2. If we take 1.5, then it is square 2.25, which is a bit larger than 2. So our number square root of 2 is trapped between them, somewhere inside the small interval. Let us make this interval smaller. We take 1.41 and 1.42. And our number is still trapped between them. We make it smaller again with 1.414 and 1.415, and it's still in there. So each time we close in on it from both sides, and each time this number is left somewhere in between. But here's what actually troubles us. We already mentioned that fractions are packed so tight that there is actually no room between them. So what is going on? There are no gaps. I could almost convince you that the line is completely full and packed. However, no matter how tightly we squeeze this interval, we can never reach the number square root of 2. We keep approaching with more and more precision, and it is simply not there yet. So how can this be possible? Is there any way to establish this number? Is there any way to actually show that this whole exists? That this is not a paradox, this is a number. We've just run into one of the small inconsistencies. This is actually where we ultimately arrive at the problem of this video, the irrational numbers. These are the numbers that bedeviled mathematicians for centuries. For the Pythagoreans, the numbers were more than just abstractions. They were just the foundation of reality itself. The discovery that diagonal of a square with each side of 1 cannot be represented as a fraction revealed the existence of such a quantity like irrational number, challenging some of their deeper assumptions. For over 2000 years, mathematicians had this riddle sitting right in the middle of it. We know that these numbers exist because they reflect the real geometry. We can drop the diagonal of our square onto the number line and see where it exactly belongs to. But we have already used up all the numbers we had, all the fractions we had. How is that possible? How can we define this void? If dividing one rational number by another gives us one more rational number, how do we finally capture the irrational numbers? We need a new perspective, something that can open our eyes to this problem from a very different perspective, different angle, an entirely new approach. And here comes the Dedekind code. Pretty fancy name, but very simple and beautiful idea in mathematics. Imagine that you take a blank piece of paper and draw a straight line on it. Then you mark 2 points on it, 0 and 1. Now you have a segment, and these two numbers, 0 and 1, are its endpoints. Now let us take another number, let's say 2. What do we see here? We now have 3 segments, 0 and 1, 1 and 2, and finally the less obvious one is 0 and 2. The first two segments are identical in length because they both represent one unit. The third segment, however, is different. It consists of 2 segments and its length is 2. In this way we can see how numbers can be represented by distances in a line. But now let us take a look at all numbers that are strictly greater than 1. What do they look like? What kind of numbers are they? They are simply numbers that are greater than 1. Let us put them into one set, and we're going to call this set A prime. For all numbers that are positive yet smaller than 1, we're going to put them into another set. Let's call this set upper A. We're going to call this set A is the lower class, and the set A prime is the upper class. This is just a matter of terminology. Now that we already decided that upper set consists of numbers that's strictly greater than 1, let us put all numbers that are smaller or equal to 1 in the lower set. Then 1 belongs to the lower set, the lower class. One may ask, so what? What is so special about this division? The special thing is actually about our A prime upper class. In fact, our upper class does not have a minimum element. What is the minimum element? The minimum element is the least element which sits in this set and which is smaller than any other element in this set. There is no such element in the upper prime class. How can this happen? Well, it is easy to show. Let us take any A prime number from A prime class. We can see that this number by definition is greater than 1. Then let's try to see the difference between A prime number and 1. We see that this difference is actually positive. There is such property called Archimedean property. It states that for any positive number, no matter how small it is, you can always find another positive number which is smaller than this positive number, a rational number. In formal notation, it states that for any positive number epsilon, there always exists such natural n that the fraction 1 over n is smaller than this positive number epsilon. This allows us to find number which is smaller than any quantity we choose. We take n to be positive here because we're interested only in positive numbers. Now we know by the construction that A prime minus 1 is always positive. Therefore always exists such natural n that 1 over n is smaller than A prime minus 1, and it is positive at the same time. Therefore this number plus 1 is actually smaller than A prime, and at the same time it is greater than 1, which means it sits in the upper class A prime, but it is smaller than any positive A prime that sits in this class. We don't have the least element. For any positive number which sits in this class, there always exists such smaller number that is also in this class. But you may object, what if we take the upper class as all numbers that are greater or equal to 1? Well, that's a good point. But in this case, we wouldn't have the maximum element in our lower class. But notice one more thing before we go even further. In our example, the number that separated the number line into two classes existed. It was 1. But now let us make a cut where the number that separates those classes is actually the length of our diagonal, square root of 2. Now we're approaching the most intriguing part of the argument. Let us take the inequality a squared is less than 2. And let us actually make a is always positive. If a is equal to 1, then 1 squared is equal to 1. Then the inequality holds. If it is 2, then 4 is greater than 2. The inequality no longer holds. Therefore, our number cannot be greater than 2. So the positive solution to this inequality lies somewhere between 0 and 2. Let us design the cut. In the lower class A, we're going to put all numbers whose square is smaller than 2, strictly smaller than 2. In the upper class, all the numbers such that their square is greater than 2. So what happens then? We have split our number line into two parts, the segment, which is positive, and the ray. Now I'm going to show you something beautiful and I'll be honest, a little bit tricky, but something that actually reveals a very important thing. Let us take the number whose square is always smaller than 2. We claim that there always exists a sufficiently small fraction, almost infinitesimal number 1 over n, that square of a plus 1 over n is always smaller than 2. That's our lower class A. doesn't have a maximum element, because this number would also belong to the set A, but at the same time it is bigger than any element of this set A. Let us actually find such n. Let us prove it. We open the square honestly. Now I'm going to use one small inconvenient observation. Since n is a natural number, 1 over n squared is never larger than 1 over n. So instead of dealing with both terms separately, we can get the following expression. Look at what we have now. If we manage to keep the right side of it below 2, then the square of a plus 1 over n is also below 2, and we're done. So it is just enough to demand the following expression, which can be simplified as follows. We assumed from the beginning that a squared is less than 2. Therefore 2 minus a squared is positive. It is a real gap and there is a room inside it. We can use Archimedean property as we used that before. The number 2a plus 1 is just some fixed constant value. 2 minus a squared is positive. So we can always choose such n large enough that 2a plus 1 over n is actually smaller than 2 minus a squared. So for such n, every inequality in our chain holds. Therefore the square of our a plus 1 over n is smaller than 2. This is exactly what we wanted. No matter which number we pick from our lower class, there always exists a bigger number in this lower class. That's our lower class doesn't have a largest element. In fact, we can apply the same kind of reasoning for our upper class and conclude that our upper class does not have a minimum element. What a paradox we have now. We have created a situation in which neither class has maximum nor minimum. How is that possible? This is exact situation where our number square root of 2 defines a cut. Such numbers called irrational numbers. They are irrationals because these two classes, they don't have minimum and maximum elements. Wait for a moment. What did we just do? We built a hole and defined the hole using our Dedekind cuts. The most fascinating thing is that no matter how hard we try, we can never fill this gap. We can approach it from below and we can try approaching it from above, getting closer and closer each time. But the gap still remains there. Using only rational numbers, we have defined a cut. And this is a little spoiler. In mathematics, square root of 2 is always either a maximum in the lower cut or minimum in the upper cut. But it is only true if we made a cut over real numbers. And this is the subject of our next video. If we only work in the rational numbers, this irrational number is never the maximum nor minimum in our classes. And this is the exact definition of a hole. Using our Dedekind cuts, we have built a very powerful tool which helped us formally define the hole, define the irrational numbers. How can we fill this hole? How can we prove that in real numbers and mathematics there are no such gaps left? This is the subject for the next video. For now, I'm gonna leave you a riddle. Do you think it is possible for both the upper class and the lower class have maximum and minimum elements at the same time? Leave your answer in the comment section below. Thank you for watching.